All right, today we're going to crack the camera's code. We're going to figure out how your phone, or a self-driving car, or really any computer with a camera, actually sees and understands our 3D world through its flat 2D lens. And spoiler alert, it's not magic. It's something way, way cooler.
So let's start with something you've probably seen. You open up an app, you point your phone's camera, and bam, there's a T-Rex stomping around on your coffee table. But have you ever stopped to think, how does your phone know the coffee table is even there? How does it know where the floor is?
Well, the secret isn't some kind of digital wizardry. It all comes down to pure, elegant mathematics. Specifically, it's about translating the 3D world you see into a 2D image using a really special kind of geometry.
To really get this, we've got to learn the camera's secret language. It's a system called homogeneous coordinates. Now, this is the key that lets a computer handle tricky things like perspective and even the concept of infinity, all with some pretty simple math.
So what are they? Well, in a nutshell, we take a regular 2D point, with an x and a y, and we just add a third number to it. It sounds simple, but this little addition is a total game changer. It unlocks this amazing ability to do really complex geometric stuff, like perspective, with simple matrix multiplication. And you know what? The conversion itself is incredibly simple. A standard point like x, y just becomes x, y, 1. That little extra 1 at the end, that's the key. It's what gives the computer a whole new dimension to play with.
And the real superpower here? It's all about efficiency. Instead of having to solve a bunch of messy equations, a computer can now find the exact intersection of two lines with just one single elegant operation. We're talking about something called a cross product. This speed is absolutely crucial for things like tracking objects in a video, frame by frame.
Okay, now this is where things get a little mind-bending. This system also lets us do something that feels impossible. It lets us define infinity. In computer vision, these points at infinity aren't just some philosophical idea. They are a super practical tool for understanding direction.
So thinking with these new coordinates, how would you actually write down a point at infinity? Let's look at three options here. Take a second. Which one do you think it is?
If you picked the middle one, you nailed it. The rule is just this simple. If that third coordinate is a 0, it represents a point at infinity. That's it. The first one is just a regular point in space, and the third one, all zeros, well, that's just undefined. So the big takeaway here is that a point at infinity isn't really a place. It's a pure direction. Think about looking down a long, straight set of train tracks. You know how they look like they meet way out on the horizon? That meeting point, that's a point at infinity. It's just representing the direction the tracks are going. Okay, so now let's use all this to decode the absolute heart of computer vision, the camera's intrinsic matrix, usually called K. The best way to think about this is like the unique digital DNA for a specific camera lens and sensor combo. Every camera has its own. Now I know what you're thinking. This grid of numbers looks a little intimidating, right? But trust me, when you break it down, it's actually really simple. It's only holding two key pieces of information about the camera, and that third row is just there to make sure all the math works out.
The first key value is that number, 2000. That's the focal length, measured in pixels. This basically tells us how zoomed in the camera's view is. It's the zoom level that's literally baked into the physical lens.
The second piece of info is the principal point. These two coordinates, 960 and 540, tell us the exact pixel that sits right at the optical center of the camera sensor. And what's interesting is that this is almost never the perfect geometric center of the image. Okay, so we've got the camera's DNA. Now what do we do with it? Well, we use it for projection. That's the process of taking a point in 3D reality and calculating exactly, and I mean exactly, where it's going to show up on the camera's flat 2D sensor. Let's make this real. Imagine a point out there in the world. Maybe it's the corner of a box on your desk. And let's say its 3D coordinates are 1000, -500, 1500. Our mission is to find the exact pixel where our camera sees that corner. And here's the calculation in action. The computer simply multiplies that camera matrix, our K, by the 3D world point. The result, after one quick final step, gives us the exact 2D pixel coordinates. That's it. That is the translation from a 3D point in the world to a 2D pixel in an image. Pretty cool, right? But there's always a but. isn't there? The catch is that the math we just did assumes a perfect camera, like a tiny pinhole. Real-world lenses are never perfect. They bend light in funny ways, which means they always distort the image a little bit, kind of like a funhouse mirror.
So, to fix this, we have to apply a distortion correction. It's basically a three-step recipe. First, the computer figures out how far a pixel is from the center. Then, it uses some special distortion numbers to calculate a correction factor. And finally, it applies that factor to just nudge the pixel back to where it should have been in a perfect world.
Okay, so this all begs a pretty huge question, right? If we need the camera's matrix K and its specific distortion numbers to make all this work, how do we actually find those numbers in the first place? Well, we do it through a process called calibration. And the process itself is actually pretty straightforward. You just take a bunch of pictures of a pattern you know is perfect, like a checkerboard, from a lot of different angles. Then, a script analyzes how all the straight lines of that checkerboard look bent and warped in your photos. And from that warping, it can actually reverse engineer the camera's exact intrinsic matrix and all its distortion numbers.
And that right there is the whole point. Calibration is the process of finding a camera's secret code. Once a piece of software knows that code, it can undo all the little imperfections of the lens and see the world with true geometric accuracy. So, from those AR dinosaurs to self-navigating robots, it all comes back to this geometric foundation. You've now seen how a machine truly perceives the world, so the only real question left is, now that you know the secret, what are you going to teach it to see next?